We are recording for differential leveling. And I'm going to pull up the lab book. Great. So we're using the exact same traverse, A, B, and C. I'm going to leave it up to you to fill out all of the other necessary requirements for the right-hand side of the page. And one thing that I forgot to do on our last one is after you do all of your calculations, you double check your precisions and everything is good. You're just going to come down here. This is after you do everything and you double check it and throw your signature on the bottom right-hand corner. So do that at the end, not the beginning. All right, differential leveling. So let's just start out with any general questions about differential leveling. All right, there's no general questions. Marcin, you have a suggestion of what, going through what's actually being input to the calculator. I do not have a connection cable to show my actual calculator steps. I'm trying to write out when I go through the calculations explicitly what I put in the calculator or written steps of what I'm doing. I'll look into actually doing a little screen calculator. I believe they have those. So I'll try to include that for next lab. That's a good point. All right. So differential leveling, here we are. Same traverse as we just did with our steel tape, but now we want to figure out the vertical elevations. Now what we've added here that we didn't have before is a benchmark. This benchmark was found looking at some plans from when they built the Cabrillo library. And it's actually pretty close to our traverse. And the elevation of our benchmark, we're going to report on our right-hand side under elevation, under station BM1. And that is 206.870. And differential leveling has a very, very some labs they don't have as clear of a setup. You don't know exactly the steps you're going to be going through, but differential leveling always has these 6 columns, which is probably why field books were designed this way. But station, backsite, height of instrument, foresight, elevation, and adjusted elevation. So make sure you have all 6 of those columns. And we know that we're going to be shooting our different points, our different stations on a traverse. So the traverse is going in a circle from the start and end station being the same. So we can set it up as benchmark 1, then A, B, C, and benchmark 1 again. Now, I know that there were only 4 stations, or excuse me, 4 setups in this particular experiment, but normally you wouldn't necessarily want to write all of your stations at first, because if there was a tree in the way, let's say that I was at setup 4 and there was a big tree between 4 and benchmark 1, I would have to do a turning point to get around that tree, and that would introduce an additional row between C and benchmark 1. All right, so let's just get to the calculations. So I went through one of these calculations in the videos. I'm happy to go over this particular one again. Does anybody, or I can go straight to setup 2. So what I have written here on the page was the math that I did in the videos. And that would be for setup 1, which is between benchmark 1 and A. So I was planning on starting at setup 2 for these calculations. Does that work for everyone, or do you want me to go through?
It works for me. I'm not sure about anyone else.
Got one person that's okay with it. I'll assume that you'll just yell at me if you're not okay with it. All right. So in the videos, we went through setup 1. Now we're going to move our instrument between A and B at setup 2. So that's going to be right in here between A and B. We've already transferred our elevation from the benchmark to A. Now we're setting up our instrument approximately at location 2. Can someone tell me what type of reading I'm going to take first? If I'm sitting there at station 2 with my instrument, what point am I going to turn my level to take a reading from?
Benchmark, some distant point.
Already taken the reading from the benchmark and transferred it to A. And now we're setting up between A and B.
So that means we'd first take the back view to
Yep.
A, and then take the foresight to B.
Exactly. So we're gonna take the back sight to A, and then turn our instrument around, go through the whole leveling procedure, make sure nothing is messed up, and take the foresight to B. So,
But do we need to focus on some distant point to avoid the parallax first?
yeah, so that would be a part of just general procedures. There's no, that's not something that you're gonna like report in your field book unless if you had some major issue, you might write a little note. But yeah, there is an embedded assumption here, I suppose, that we are doing all of the standards and practices, such as parallax reduction, when we set up our so let's assume that we did all that. Everything's perfectly. Our bubbles are level. Everything's wonderful. We set up at station 2. We turn around to A, take a back sight. And the back sight that we get, we're going to estimate to the thousandth place. And what is it? Let me find my data. I misplaced it. There we go. It is 3.692 feet. And then our rod person goes to A, or excuse me, they go from A to B. You get everything set up. you turn the instrument around, do all of your checks to make sure you're level, and you take a reading from the rod at B. Reading is 3.670 feet. So, what do we need to do in order to figure out the elevation at B?
We need to add the back sight to the height, and then subtract that by the foresight to get the elevation.
Yeah, exactly. So that's the math. We're gonna take that elevation on a back sight up the rod and add it. That's gonna give us the height of the instrument. And then we're going to subtract off the foresight to get the elevation at B. So could someone do the first calculation to figure out the height of the instrument at station 2?
And I just have a request as well. It's a little easier to sometimes see it on the side view. So if you don't mind drawing it out maybe as well, if that would work.
Yeah, definitely. I'll draw that out here in a minute because it is a little confusing without seeing it a couple times. Mason, you said, oops, it looks like, yeah, maybe you subtracted.
I got that too, Mason.
It happens to the best of us. So that tells us our height of our instrument. And then we transfer that back down to B by subtracting off the foresight. So what is our elevation at B? So Mason, you're saying 213, but remember we're subtracting off our foresight from the height of the instrument. I'll draw a diagram of this just to make sure that we understand how these elevations are being transferred. So we're going to actually want to do a subtraction. We're going to want to take height of instrument minus it, 206, 652. This is a great opportunity to draw a schematic, and I am also, visual person a lot of times. So let's just go through this little side view. So A to B, there's not really that much elevation change, but for the sake of it, let's draw it like this. So here's point A, and that has an elevation of 206.630 feet. And we're trying to figure out the elevation at B. And we have our instrument that has some height above mean sea level. So what we're doing here is the profile view, I like to think of it as we're transferring an elevation. We're taking this elevation at A and we're using some readings in order to move that elevation to B. So how does that occur? We take our rod at A. We have a bunch of readings. And then we take the rod to B. And what are those readings physically? Well, they're like this. Our back sight is here. And we're just reading some elevation off the rod. So this is our back sight. So really that label should just be there. That's our back sight reading. It's just that point on our rod. So all we're doing is we're moving that elevation up the rod, transferring it across to our instrument. We're just adding it to the elevation at A. A plus back sight is the height of the instrument, right? Now we're going to turn our entire setup around and move that elevation to point B. How do we do that? We take a reading on the rod, and that is our foresight. Now, that foresight needs to get moved down the rod to point B, and that is our elevation at B. So mathematically, what does that look like? That means that our height of instrument in this case is elevation at A plus the back sight, and then our elevation at B is just equal to the height of the instrument minus the foresight. Is this generally helpful to everyone to see it like this, to see the geometry of the thing? Great. Excellent. So I think about it like physically what's happening is we're taking a rod reading, we're moving an elevation up, we're transferring it, we're transferring it across through the instrument, and then we're using a reading in order to bring that elevation back down. So it's like up, across, down. Cool. And that's kind of why we set up the field book in this way. It's trying to give us like in a table like a physical idea of what we're actually doing. Great. So that is the equation, or that's the data for B from A to B. So that'd be setup 2. So let's move to setup 3. We set up at 3, we do all the necessary things, and we turn our instrument around. If we're sitting here at station 3, what point are we gonna take our back sight from?
To B?
To B, exactly. And that back sight is 4.589 feet. Turn the instrument around. Take our foresight to C, which is 7.2 361 feet. Can someone do the math to tell me the height of the instrument?
I'm sorry, can I ask you one more question?
Of course.
Why do we need to calculate the height of instrument at all? If we just write it in a way, elevation at B equals elevation at A plus the difference between backside and forward side. We don't actually need the height of instrument, do we? That's
Mathematically, you do not need the height of instrument, no. The reason that you want to keep the height of the instrument is that it makes it very clear about what measurements are being taken and what elevations are being transferred. So it comes down to a reporting issue, not so much a math issue.
okay, thank you.
Yeah. So this would be one of the cases where I would say you can't just use whatever math you want. This is a very differential leveling is a very prescriptive activity. All right. Oops. Gosh dang it. Okay. So someone mentioned in the chat our elevation 211, 241. Exactly, which gives us an elevation of what? At C. 203.880. Don't forget that last data point. All right. So from C, that's it. We have A, B, and C. What do we need to do to complete our traverse? We need to get back to the benchmark. And hopefully it is the exact same value as what we started with. So we're going to set up at 4, and we're going to take a backside to C. And we're going to turn the instruments around and take a foresight to the benchmark. We were very careful in how we set things up for our lab. So we knew that we would have a clear sight from C to the benchmark. But a lot of times you'd actually have to do another setup turning point to get from C to benchmark 1. So we take a foresight to the benchmark, and we get 5.390 as our reading. So what is our height of instrument? $212, $249. And what is our elevation of our benchmark at the end of our traverse? 206,859. All right, 206.859, and our original was 206.870. So is that acceptable? Well, let's do the calculations about whether or not that is acceptable. And the first thing that we need to do is calculate our closure, and we have to do that in two ways. We do it by looking at benchmark initial minus benchmark final. And we also do it through the sums of the back sites and sums of the fore sites. And why do we do it this way? It's just a mathematical check. These two equations should yield the exact same number. So this is just a math check for us. So if we add together all the back sites, we're going to report that here. So if someone can start on that math, and then we'll need all the sum of the fore sites. We'll report that here. And then in addition, we need benchmark initial minus benchmark final. And then we'll report that down here. So if someone could do that math as well and plug it in. Back sites 21.455. Mason Luis, thank you. What about fore sites? Or the benchmark initial minus final. As soon as you get it, just throw it in the chat. Excellent. Stella, Luis, Mason, yep, you're all getting the same number. Good stuff. All right, so let's do the next one. Now we're going to do the math check. The sum of the back sites minus the sum of the fore sites. Point 0.011. And I should mention, I didn't write it here, my bad. We're going to report these as absolute values. Or alternatively, actually, you know what? We're not. Scrap everything I just said. I just realized I made a little mistake. So, again, my mistake, I should just cross it out. It's actually benchmark final minus benchmark initial. There we go. So yeah, negative 0.011. What about the benchmarks? So that would be this value here and this value here. Minus point, yep. So Mason, maybe, yeah, just check the math. So in this case, it is negative 0.011 feet. And those are those equal? Yes, they are. Great, our math check is good. All right, and for this particular project, our allowable closure is equal to 0.010 feet times the square root of the number of setups. So our number of setups is 4, square root of 4 is 2, 2 times 0.010 is equal to 0.020 feet. And 0.011 is less than that. So we can write a little note. Enclosure, this should really be plus or minus. Plus or minus. Great. All right, so there's one last thing that we need to do in calculating is doing our adjusted elevations. So adjusted elevations, there's lots of different ways of doing it. We're going to kind of do it the simplest way, which is we're just going to, it's essentially a weighted average. So the farther the distance between any two stations, the more adjustment we give to that elevation. So in order to do that, we have to know the length from benchmark 1 to A. So you could just paste that. This is not a highly precise method. We're just trying to generally adjust the elevations such that our traverse begins and ends at the same elevation. So I need a little bit more room. So I'll go to my right-hand side and just say benchmark 1 to A. That length is equal to 34.06 feet. And the length of our circuit, well, this is the exact same traverse that we did in lab 2. So our total length, L, if you do all the math, adding it all up, is 320.556 feet. All right. So how do adjusted elevations work? So the adjustment that you give, so for example, point A is equal to this equation. So let's break this equation out a little bit farther on a new page. That is equal to E times benchmark to A over length of circuit, where E is equal to closure error. In this case, negative 0.011 feet. Now, our adjustment to point B is just equal to that closure error, benchmark to A, plus A to B, over L. So let's just look at this first case and do the math for it. So our error is 0.11 feet. Benchmark to A, 34.06 feet. And the length of our circuit, 320.556 feet. So someone could plug that into their calculators and tell me what that is. All right, and some answers rolling in, and they all look to be what I got. And that is, in this case, negative. So here's the trick for this, is that since we ended lower than our actual elevation, we have to add in order to get our adjusted elevation. So this negative means that we were lower than expected. So our adjusted elevation at A is just equal to elevation at A plus 0.001. In this case, we can only go to the thousandths feet. Is that, it feels a little arbitrary, and it's because it is a little bit arbitrary. So without doing any math, this is a no math question. What is our adjusted, what would be our adjusted elevation at our benchmark final? So think about what we're doing here. Look at this equation where we're saying error times the ratio of how far we've gone in the circuit to the total circuit. So same for B. We're just multiplying that error by the ratio of how far we've gone in the circuit over the total circuit. Where did I get benchmark to A? I don't remember. I either pasted it or I got a piece of steel tape and I just did a kind of quick measurement. It's just something you would do in the field. So yeah, benchmark to benchmark. So benchmark is the same. Exactly. Just equal to BM initial. And mathematically, why does that make sense? So C to BM final, that's just the error times benchmark to A to B, B to C, C to A to benchmark. That's over the total length of the circuit. Well, the numerator is the length of the circuit. So this is 1, which means that we are giving all of the error across the entire traverse to our benchmark final. So that is our mathematical check for our adjusted elevations. Is that our adjusted elevation at benchmark 1 has to be 206.8708. And let's just write one down because we just did. A, that was 206.6318. And that's it. So I'm going to leave the last two calculations for the adjustment of B and C for all you to do. If there's any final questions about differential leveling that are applicable to everyone, yeah, let me know. Otherwise, I'm going to stop the recording. I'll get these posted hopefully by, I don't know how long it takes for them to upload to the cloud, but hopefully by either this evening or tomorrow morning. And that's it. That is taping and differential leveling. I hope that this has been not too terribly awful. All right, if there's no questions that are applicable to differential leveling in general, I am going to stop the recording, and you're welcome to stick around and ask me anything more specifically.